Now let us consider another application of Newton's laws. Sloping roads, freeway on and off ramps, and ramps used to load trucks are all forms of inclined planes. An object resting on an inclined plane is subject to the gravity force. However, unlike a flat ground, the force of gravity has a component along the surface of the ramp, causing the object to accelerate down the ramp. Because of the geometry of the inclined plane, it is convenient to rotate our coordinate system so that x is along the incline and y is perpendicular to it. In our new coordinate system, the force of gravity is given by minus mg times the sine of theta in the x direction, minus mg times the cosine of theta in the y direction. Using Newton's second law, we can write the sum of the forces in the x direction as the mass times the acceleration in the x direction. The only force acting on the crate is gravity, with a magnitude of minus mg times the sine of theta. Striking out the m's on both sides gives us the acceleration down the incline, which is minus g times sine theta. Note that this acceleration is independent of the mass of the object. Since this incline has an angle of 30 degrees to the horizontal, we can calculate the horizontal component of the acceleration of the crate to be negative 5 meters per second squared. If the force of gravity causes an acceleration in the x direction, what happens to the force of gravity in the y direction? Correct. There is no acceleration in the y direction, and Newton's second law in the y direction can be written as follows. Now let us consider the case of pushing a crate up an inclined plane at an angle of 30 degrees to the horizontal with a constant horizontal force of 150 newtons. Now the person pushing the crate must overcome the force of gravity to push the object up the plane. The force diagram is as follows. The horizontal force exerted by the person has components in the positive x and negative y directions. This force makes an angle of 30 degrees to the x-axis. Recall that gravity had components along the negative x and negative y directions. The normal force is in the y direction only. Newton's second law in the x direction now contains a component of the force exerted by the person and the component of gravity in the negative x direction. To calculate the acceleration of the crate up the inclined plane, we plug in 150 newtons for the force exerted by the person, 10 kilograms for the mass of the crate, and theta equals 30 degrees. After some arithmetic, we obtain a horizontal acceleration of positive 8 meters per second squared. Recall that the positive x direction is up the inclined plane. What if the man pushing the crate wanted to do so at a constant speed? How much force would he need then? You can use the example we just did to answer this question. Correct. To solve this problem, we start with the force equation in the x direction and set it equal to 0, since constant speed means 0 acceleration. We then solve for the force and plug it in to obtain 58 newtons. Earlier in this lesson, we briefly talked about friction and its effect on moving objects. Friction is a force that exists between two objects that are in contact with each other and always opposes motion. The amount of friction between two objects is characterized by the coefficient of static friction μ, which is usually a number between 0 and 1. There are two varieties of friction forces. Static friction is a frictional force which prevents objects at rest from moving. The magnitude of the force of static friction is given by the coefficient of static friction times the normal force, which, on a flat surface, is equal to the weight of the object. The subscript s on the μ denotes static friction. Once we exert enough force to overcome static friction, we have to deal with kinetic friction, or rolling friction. The formula for kinetic friction is similar to that for static friction. We denote the coefficient of kinetic friction with a subscript k. Usually, the coefficient of kinetic friction for an object is much smaller than the coefficient of static friction for that object. In other words, once an object starts moving, it requires less effort to keep it in motion. Let's revisit the inclined plane, this time taking into account the frictional force. Recall that in the absence of friction, the object slid down the incline because of gravity. Now the force of gravity has to overcome the force of static friction to move the object down the slope. The forces acting on the stationary crate are gravity, pointing downward, the normal force, pointing in the positive y direction, and the force of static friction pointing up the plane, positive x direction. Let's begin with the y component of the forces. This equation is the same as the one we obtained in the absence of friction. We can solve this equation to obtain the magnitude of the normal force, which we will need to get the frictional force acting on the crate. The x component of the net force has the force of gravity plus friction. Does the mass accelerate down the plane? That depends. If the component of the force of gravity can overcome the force of friction, then the object will move. The critical angle where this occurs can be found by setting Fx equal to 0 and solving for theta. One last topic to consider is that of pulleys. Pulleys are devices that change the direction of the tension force in cords connecting objects. Consider the two objects connected by a massless cord over the pulley. The forces on block number 1 are gravity pointing down, the normal force pointing up, and the tension in the cord pointing away from the block to the right. The forces on block number 2 are the force of gravity pointing down and the tension force pointing up. Because the cord connecting the two blocks is massless, and because we assume the pulley to be massless and frictionless, the two tension forces are equal in magnitude. The change in direction of tension occurs because of the pulley. Let's write the components of the net force for both blocks. For block number 1, we examine the x component of the force, which is given by Fx and is equal to the tension force, which is equal to the mass of block number 1 times the acceleration of the block. For block number 2, we have forces in the y direction only. These are gravity and the tension force. We therefore write the sum of the forces in the y direction as the tension force minus the force of gravity, and this equals the mass of block number 2 times the acceleration of the block. We have two equations and three unknowns: the tension force, the acceleration of block number 1, and the acceleration of block number 2. How do we get rid of one of the unknowns to be able to solve these equations? Correct. Since the two blocks are connected by a finite length of cord, the magnitude of acceleration is the same for both blocks. We can now solve these equations by substituting for the tension force in the second equation and solving for the acceleration. So the acceleration is a fraction of what it would be if block number 2 was falling due to gravity.